Today we're going to talk about my favorite conic section, the parabola. And you've worked with parabolas in the past during high school and also during your pre-calc or college algebra courses, but you may or may not have looked at the two pieces that actually help to create the parabola, which is the focus and the directrix. If I have my parent function for y equals x squared, when you begin to study parabolas, you start with the actual parabola, and you spend a lot of time talking about the vertex and the axis of symmetry. That axis of symmetry is actually what starts our parabola, not something that we just happen to find after we have already drawn the parabola, but it starts out as a line segment. If I have a point and a line, and I drop in a perpendicular line from that point to the line, and I create that small segment. In the middle, I can find my midpoint, and I'm going to make that the vertex of the parabola, like this. And so I have this little section right here. I can find the locus of points that are equidistant from both the focus and the directrix, the point and the line, and that locus of points is the creation of the parabola. So if I take this midpoint and drag it so that the distance from that point as it travels back to the focus, or as it travels from back to the directrix, remains equivalent, then I create the parabola. And here's a nice little animated GIF to show you what's going on. You start with the focus and you have your directrix. You drop in that line, you find the midpoint. That's obviously going to break it into 2 points. As that vertex begins to travel, if you want to maintain an equal length, that's how you get your parabola. So it's pretty cool. And it's something that we don't really talk about, the focus and the directrix, until you actually have a better understanding of the parabola itself. Meanwhile, it's that focus and directrix that help to create it. Normally when we look at these, we look at either the standard form or the vertex form. And the vertex form is really helpful when I'm graphing these because it's very easy to see where your vertex is, and it's easy to pull out what's going on with the width of that parabola. And one of the nice features between the vertex form and the standard form is the fact that that A value stays the same, which is something that doesn't always happen when we're dealing with one form of equation or the other, but A from the vertex formula is the same A value from my standard form. Now, in standard form, you can't see HK, and in vertex form, you can't see BC, but all those numbers are in there of either being factored or distributed out. When we're talking about the focus and the directrix, those values are also hidden in there, but we're going to be able to pull those out. Depending on what video and what textbook you look at, they may change up that formula in different ways, and they may use different variables. Essentially, what they're always going to do is take that A value, and they're going to make it equal to either 4c, or in this form that I have written here, it would be equal to 1 over 4c. Unfortunately, the Sullivan textbook uses an A value, but that's not the same A value as the standard form or the vertex formula. So I tend to write a C just so that we don't get confused. And the other conics, like the ellipse and the hyperbola, will use a C value for distance. On top of that, our textbook does not write it where the coefficient is on the term that's squared, but on the other side, like this. And so it would pull this A out and put a 4c over onto the other side. I'm going to pull up the PowerPoint, and we're going to use that PowerPoint to look at some examples, but we're going to go in a little bit of a different order than they have suggested. So here is the form of the vertex formula that they use when they're looking at the different parent functions that create the different parabolas. So you can see that the squared term on the x here, but notice that there's no coefficient. It's over on the other side, and unfortunately they're using an a. That is not the same a from ax squared plus bx plus c. 4a would be equal to 1 over that a value. So we tend to look at it, if we were looking at it from the way that we're used to it, it would be over here like this. But this textbook has it in a little bit of a different order, so we're gonna do what they want us to do for a change and use their formula. Now they offer up two different formulas, one where the 4a is positive and one where the 4a is negative, but it's the same situation as before. If the coefficient that, regardless of what term it's on, whether it's on just the y or on the x squared, if it's negative, then you have a situation where your parabola is opening down. If the coefficient of that binomial term is positive, then it's going to be opening up. And so nothing else really changes there. But now we're going to be able to start talking about parabolas that have seemingly fallen over. So before, when we looked at those types of equations, it was when they were the inverse function of the x squared. And then we would restrict the domain so that way that inverse function actually stayed a function. But now that we're going to be able to work with these in a couple of different ways, we're going to allow that domain to become unrestricted, and we're going to have a sideways parabola. And you can see not too much changes other than what gets squared. So if your y is squared, it's going to be opening up left or right. If your x is squared, it's opening up or down, like the way that we're used to seeing our parabolas. Same rules apply. If it's a negative, then it's going to be opening left, because that's the direction that our negatives go. And if it's a positive that's in front of that binomial term, then we're going to be opening to the right. The focus is always inside of the parabola. The directrix is always on the outside. The vertex and the focus will share the same x part of the coordinate, so they'll both be on that axis of symmetry. The axis of symmetry will always be perpendicular to the directrix. So let's look at an example problem. We'll start with our up and down parabolas, just help us gain some perspective on how these things work, and then we'll look at some left and right ones. Let's analyze the equation x squared is equal to a negative 12y. So when I first get equations with conics where I have x's and y's squared, the first thing you're going to want to do is say, well, what kind of conic am I looking at? And if only one of the terms is squared, just the x squared or just the y squared, then you're talking about a parabola. If the x is squared, then I know I'm talking about the one that I'm used to talking about, the up and down one, like this. And if I kind of want to get an idea of what this really looks like, I can move the coefficient that this textbook is going to put on the y back over to the other side. So I know I'm talking about a really wide parabola. A negative 1/12 x squared is equal to y. It's not uncommon for these parabolas to be very, very wide. So I know that I am looking at an equation that is going to be in the form, and we'll get this out of your way so that you could see it, of the negative 4a. I know that 4a needs to be negative because if I rewrite it to the way that I'm used to looking at it, I have a negative 1/12 x squared equal to y, so I know that it's opening down, so I know it's this one. And so that my coefficient has to remain negative, so this is a negative 4a. Well, if I take this term that they're saying is equal to a negative 4a and set it equal to this, I can easily find that a value. Negative 4a equal to a negative 12. That leaves me with a has to be a 3. That value that you find, which I was calling c on the other page because it's a different a from this negative 112 from the ax squared. That is the distance that your focus and your directrix is from the vertex. So if you were standing at the vertex, you would have to take 3 units into the parabola to stand on the focus, and you would have to take from the vertex 3 units out to then draw your line. Where is this parabola located? It's at the vertex because I don't have any binomials in there, right? It's not x minus something squared. It's not y plus something. So I know that I'm at the vertex. So from the vertex, I would have to go down 3 to get to the focus. So the up or down of, you're going to have to go in and out. So which way is in? Well, I'm facing down. So if I go down, I'll land on the focus. And so then my focus has to be at 0, negative 3. If I step 3 out of the parabola, well, out's going to be up. And that will land me on the directrix. So I have a graph that looks like this. Now, if I were going to, I call it a tabletop, although we're upside down here, so it would be more like a floor. If I was at the focus, going to draw a line that is parallel to the directrix from the focus, that goes through the focus, and then intersects into the parabola. So kind of like a circumference, right? You're going through the center and you're hitting the diameter, right? You hit the circumference and you're going through the center. Same idea here. That is called the latus rectum. Now you know the equation for the parabola, and if this is on the line, if these 2 points that are on the parabola have to be on the same y equals line as this focus, then you know that they also have to have a y component that's a negative 3. So I could very easily say, well, if y is a negative 3, I can plug it into here and find out what the x part of those coordinates would be. So when you're working through these, direction's going to be important. I'm going to go backwards and look at the y squared equal to an 8x. So I have another one that is just an x squared or just a y squared. So I know it's a parabola. The y is squared, so I know it's a left or a right. Now I look at the coefficient, and the coefficient is positive. So I know I'm opening to the right, and it looks something like this. That coefficient I'm going to set equal to 4a and solve. And when I find my a value, that a value of a 2 tells me how far away the focus and the directrix are from the vertex. Now the vertex you're going to be able to see right away because all of these questions are going to be in the vertex form, or you're going to have to put them into vertex form. So since this is essentially in vertex form because it's centered at the origin already, I know I'm at 0, 0. But now if I want to walk into the parabola to place my focus, I have to walk in to the right. So 1, 2 to the right. And so that would land at 2, 0. And if I want to go 2 out, out is to the left. So I'd have to come out 2 units that way. And from the origin, that would put me at x equals a negative 2. If I want to find the lattice, I'm going to kind of put up a wall that anchors to both sides of the parabola but goes through that focus. Well, if it goes through the focus, this will always be parallel to the directrix, and if this is an x coordinate of 2, then these also have to have an x coordinate of 2. And if x is 2, I can plug it into my equation and find y and find the other 2. Let's move these around a little bit and look at parabolas that don't have a vertex at the origin. So when we move them around, all of those statements are still going to remain true. That a value is going to still be how far away you are from the vertex to the focus and to the directrix in and out. Directrix will still be out. The lattice, although we tend not to ask about that as much when we're not focused at the origin, will still be parallel. Let's find an equation of a parabola that has a vertex at a negative 2, 3 and a focus at 0, 3. So maybe the easiest way to begin these is to start to think about what direction that you're facing. Now they kind of prompt you down here at the bottom. Of course, that's not going to happen when you're either taking a test or out in the real world. So you're going to have to plot this. I have a vertex at a negative 2, 3. 1, 2, 3. And I have a focus at 0, 3 right here. All right, so if this little dot to the left is my vertex and my focus is at 0, 3, I'm opening up this way because the parabola will always hug around that vertex, the focus. So I have HK. I know I'm opening to the right, which means my parabola has to have a y squared, which is why they chose this. And I know that since it's right, the coefficient in front of the x term has to be positive, and that's why they chose the positive 4a. Well, I have HK, so I can plug that in. You flip those values every time you plug them in because you can see that the negative is a part of the formula. So it'll be y minus the 3 squared, and then I have 4 times, and we'll talk about this 2 in a second, x minus the negative 2. Where did they get the 2 for the a? They just counted. If I was at negative 2 for my vertex, and then I went to the focus and I was at 0, I had to move to the right 2 units, and so we'll just put in the positive 2. And so I have the 8. And then you already have your equation. You're all finished. If you wanted to find the lattice, well, you know that the focus is at 0, 3, and the lattice would have to be sharing that same x coordinate since we're putting up a wall and not a floor or a ceiling. So you could plug a 0 in for the x and solve for the 2y values that would land on that parabola. Like that. Sometimes they're not already set up for you to go and get ready to go. So we'll need to look at this and clean it up and do the dreaded completing the square. I have an x squared plus a 4x minus a 4y. All right, so I got x squared, not a y squared. So the good news is that I'm talking about our old parent function, y equals x squared. They like to put the 4a over here, but we're going to have to move these around a little bit. Let's bring the 4 over to the other side, the 4y. So I got x squared plus 4x equal to a 4. When you complete the square, add in this little blank. And then we're going to do the same thing on the right, because whatever you add to the left, you have to add to the right, or else it's not going to be equal to anymore. And it will always be an equal, because if you're squaring this number, whether it was negative or positive, the number that gets placed on both sides will have to be positive. What number is that? It's the number that will allow you to factor this trinomial into a form of x plus or minus that number, that quantity squared. And so what will always work is if you take the b value, divide it by 2, and square it. That's the number that's always going to get added in on both sides. And so I'm going to add the 4 to both sides, and then I'm going to start to factor everybody. Of course, the left's going to factor into an x plus 2, that quantity squared. Over on the right, I'm going to be able to factor out the 4. This is now equal to a 4a, which means a needs to be 1. Go to your vertex, and you're going to count 1 into the parabola, which is opening opening up to get to your focus, and then you're going to drop 1 out of the parabola to get to your directrix. And there's your equation. You would do the same thing if it was opening left or right. It's just you would complete the square in the y term instead of the x term.